Swayam Prabha. Digital India. Educated India.
So, hello everyone. Today we will discuss about the adhesion and cohesion. This is the sixth lecture, or you can say third lecture in the module 2. So, first we will quickly summarize about the last lectures. In the last lecture we discussed about the wettability, we discussed about the contact angle, then we derived how the different surface tension at different interfaces, solid liquid, solid vapor as well as the liquid vapor are related through the Young's equation. Then we define the surface hydrophilicity or hydrophobicity in terms of the contact angle. Then what should be the criteria of the spreading. Followed by that we discuss the effect of chemical heterogeneity as well as the physical heterogeneity. So, chemical heterogeneity we discussed through the Cauchy equation, and physical heterogeneity we discussed through Wenzhel equation in terms of surface roughness. Also we saw because of various heterogeneity in the surface we observe the contact angle hysteresis, and it gives some useful information about the surface heterogeneity or some changes in the surface energy of the solid surfaces. So, in today's lecture we will start with what is adhesion and what is the cohesion. Followed by that we will just see interaction between the two liquids, that is sort of cohesion, and then solid liquid interface, the adhesion. Then followed by that we will quickly see how this intermolecular interaction during the cohesion and adhesion takes place, particularly in terms of work of adhesion and the surface tension or surface energy. Then we will see the example of two particle particle interaction and particle surface interaction, considering the presence of van der Waals interactions. So, first thing, as we have discussed in the previous lectures as well, the work of adhesion between two phases A and B is surface tension of A plus surface tension of B minus interfacial tension between A and B. So, I have seen this is the work of adhesion. Adhesion we call when A is not equal to the B. We call cohesion when A equal to B. So, if there is a interfacial interaction between 1 and 2 we call the adhesion, but if it is between 1 and 1 we call as the cohesion. So, if you recall the last lecture, so in case of either adhesion or cohesion, the work necessary or change in free energy required to separate the unit area of the interface, that interface may be either the liquid vapor or the solid vapor interface. So, for the change in, or you can say to the create the unit area, the work done or free energy change is the work of adhesion. Now, as I discussed, if it is between the same media it is called cohesion, if it is different media it is called the adhesion, and these both adhesion and cohesion occurs because of the various intermolecular interactions, as we discussed in the first module. It may be the van der Waals force or electrostatic interactions. Now, let us consider there are two liquids A and B. So, B is interacting or spreading over A. So, B is interacting or spreading over A. There will be A, B and AB. In this way there will be 3 different area, change in the area of A plus change in the area of B plus change in the area at the interface AB. Now, if you want to calculate the total free energy delta G, so it will include all 3 components, delta G upon dA, change in the area of A, dou G upon dou AB, change in the area of interface, dou G upon dou A, change in the area of B. So, in this way we are going to have 3 components A, AB and B, and as we remember we simply define surface energy as a dG upon dA at constant T, P and N. So, we are considering here the constant temperature and pressure. So, if there is a interaction between A and B, so change in the area of B will be minus of the change in the area of the A, and that area should be same as change in the area of the interface. So, if you consider this, so dAA will be minus dAB and dAAB will be again. So, this will be minus dAB, this will be dAB again and this. So, let us consider the spreading coefficient dG upon dAB in terms of free energy change for the spreading of B over the A, spreading of B over the A. So, dAB will be common. So, you will end up over here is gamma A minus gamma B minus gamma AB. So, what it says is the spreading coefficient is the difference between surface tension of A minus surface tension of B minus interfacial tension of AB. The same thing we discussed in the last lecture as well, where we discussed in terms of liquid vapor. So, if you consider in terms of solid liquid or in terms of liquid vapor, you should be able to, so that we will discuss in terms of the adhesion. So, here we are talking AB in terms of adhesion, it will be the as solid versus liquid. But here what is happening, there are 2 liquids are coming in the contact. So, with time they will become mutually saturated. What does it mean? It means there is a change in the composition. If there is a change in the composition, it means the surface tension or surface energy is going to change. So, let us say gamma A changes to gamma A B, and similarly gamma B changes to gamma B A. So, accordingly if the surface tension of A and B is changing, it means the spreading coefficient is also changed. So, we define spreading coefficient B A upon A. So, it means here we are considering the change in the surface tension of the gamma B. So, it will be like a gamma A minus gamma B A minus gamma A B interfacial tension. Similarly, we may consider the change in the surface tension of the both A as well as the B. It means A is also saturated with B and B is saturated with the A. So, in this case it will be gamma AB minus gamma BA minus gamma interfacial tension. So, in this way we should be able to calculate the spreading coefficient of one liquid over the other liquid. So, here I have listed spreading coefficient of various liquids and the water. So, if you see starting from the higher alcohol, isoamyl alcohol 44, it is going to the benzene 8.8, toluene 6.8, going to hexane 3.4. Now, but from here onwards it is going in terms of negative, ethylene dibromide, methylene diiodide, bromoform, iodobenzene, carbon disulfide, they are having the negative spreading coefficient. So, what does it mean? In case of negative spreading coefficient means there will be no wetting. So, up to you can say hexane to the higher alcohols, they will spread on the water, but for these where you are getting the negative value of. So, you can say if you want to have the spreading, the value of S B A, it should be greater than 0. If it is less than 0, there will be no spreading. Now, let us as we discuss, this is the ideal case when the purity of A and B are intact, but in practical when the two liquids are coming into the contact, they are going to mutually saturate each other. So, their composition or purity is going to change. So, let us consider a case of benzene and water system. Their interfacial tension is given as 35 millijoule per meter square. Surface tension of water is 72.8, but after getting saturated with B, as I told, it is going to decrease. So, it is decreasing to 62.2 millijoule per meter square. Surface tension of benzene is as 28.9, and when it is saturated with water, it is decreasing to 28.8 millijoule per meter square. Now, if we calculate the spreading coefficient before saturation and after saturation. So, if you want to calculate spreading coefficient before saturation, so it will be very simple. SBA, surface tension of water minus surface tension of benzene minus interfacial tension, its value is coming out to be 8.9. Now, if you want to calculate the surface SBA, we are only considering the benzene is saturated with the water. So, here it will be surface tension of water minus surface tension of the benzene saturated with the water minus interfacial tension, it is coming to be 9. But interestingly, if you calculate the spreading coefficient of benzene is saturated with water and water is saturated with the benzene. So, it will be like, now here is a decrease in the surface tension of the water, it will be 62.2 minus decreased surface tension of benzene 28.8 minus interfacial tension. So, it is coming out to be the negative. So, what it says, the first step will be spreading if it is positive, and once spreading, then there will be the saturation, and after saturation, as it is coming negative means there is no spreading, or you can say there will be, it will retract, it retracts. So, these are the three steps: spreading, then saturation, then retractions. So, this happens if two liquids are interacting with each other. Now, let us consider the case of solid liquid interface. So, this is the solid, we are going to have solid vapor, surface tension, we are putting a drop of liquid, it will form certain contact angle, and based on the contact angle we should be able to comment whether it is a hydrophilic or the hydrophobic surface. So, the liquid is having the surface tension of gamma LV, and this is the interfacial tension between the solid liquid gamma SL, and this relation we can define, or you can say the contact angle we can define using the Young's equation which says cos theta is equal to gamma SB minus gamma SL divided by the gamma LV. And here again similar to the cohesion, we can calculate the spreading coefficient gamma SL. So, gamma SL will be gamma SV minus gamma LV minus gamma SL. So, if you remember the last slide, we calculated the spreading coefficient as the difference between the work of adhesion and work of cohesion. Work of adhesion minus work of cohesion. So, here this criteria will remain same. If the value of S is greater than 0, it will spread the completely spread on the surface. If it is less than 0, there will be no complete spreading. So, this is about how the adhesion and cohesion takes place. Now, we will just see how we calculate the work of adhesion. So, work of adhesion between 1 and 2 is the work required to separate the unit area of the interface, and we W12 is surface energy of 1 plus surface energy of 2 minus the work required. This much work is required to separate the unit area of the interface minus gamma 12, or you can say the surface energy of 1 plus surface energy of 2 minus interfacial energy. And if it is 1 in case of cohesion, the work of adhesion will be twice of the surface energy. The work of adhesion, so this is the, you can say the work of adhesion, this is the cohesion, this is we say adhesion and this is cohesion. So, here Giri-Falco and Good assume the geometrical mean rule for the work of adhesion is twice of the surface energy of 1 into surface energy of 2 to the power 0.5, and also they added one constant. Now, as you know, the surface energy of a liquid or a solid has a two component, polar as well as the dispersive component. So, here gamma 1 will be gamma 1 dispersive plus gamma 1 polar. Similarly, gamma 2 will be gamma 2 polar plus gamma 2 dispersive. So, we can expand again W12 is 2 the psi gamma 1 dispersive gamma 2 dispersive to the power half plus gamma 1 polar gamma 2 polar to the power half. Now, this psi is a function of the molar volumes of 1 and 2, and typical value of psi I have listed here for the alkanes. Its value is about 0.55, aromatic hydrocarbons it is about 0.7, for polar liquids it varies between 0.6 to 0.9, and for hydrogen bonding compound its value is 1. So, in most of the cases we consider phi as unity if we assume that molecular diameters obey a geometrical mean law. The molecular diameter of 1 and 2 is following the geometric mean law, then we take the value as unity, and this is a typical range. So, if you consider most of this polar liquid as well as the hydrogen bonding compounds, it is very close to 1. So, in most of the cases you will see we mostly consider the value of phi as 1. So, from the work of adhesion we can calculate the interfacial tension will be the gamma surface tension of 1 plus surface tension of 2 minus this is the work of adhesion. And in case of solid liquid interface, 1 will be your solid, 2 will be the liquid. So, the same expression can be written in terms of solid liquid interface. So, it says gamma solid liquid is equal to the surface energy of the solid plus surface energy of the liquid minus work of adhesion between the solid and liquid. So, depending on 1 and 2 we can write solid liquid here. So, I have listed few examples of adhesion particularly in biological systems. So, one example is the adhesion of blood cells or blood platelets to the injured blood vessel and it prevents the bleeding. So, if the blood platelet cells adhere on the blood vessels, it prevents the bleeding. Now, but again at the same time the blood platelets on the medical implant devices, then it causes clotting or you can say the thrombus formation or the biofouling. So, it may have the positive impact as well as it may have the negative impact as well. In most of the cases, if you just see the cell adhesion and growth particularly in the tissue culture, it is stimulated by the attachment of cell to the surface. So, they are the surface adhered cells, particularly mammalian cells. If you see a tissue culture, they are like kind of surface adhered cell. They first adhere on the surface, then they grow. So, particularly if you just see you are having various bone implant or teeth implant, dental implant, there again there will be going to be adhesion of the cells. Also, if you see the formation of biofilms on a particular surface, there will be formation of the biofilm. It is a bacterial biofilm. It may again cause the biofouling or it may again cause the infection, but again the biofilm if it is forming in the wastewater treatment plant, especially on the some support, the biofilms are also used for the wastewater treatment. But in case of biomedical, if the biofilm is formed, so we call it a bacterial biofilm, that is not desired. So, we can say various adhesion phenomena are there in the biological system, starting from the in vivo body system. In case of injured blood vessels, there are blood platelets and they stop bleeding, but when they attach on the particular biomedical implant, they causes thrombus formation or the clotting. Also, the cell adhesion and growth particularly in the tissue culture is stimulated by attachment to the surface, or you can say they require some sort of anchorage and adhesion of cells on the biomedical implants like teeth, dental and bone implants, and of course, the formation of biofilms on any surface. So, these are the few examples where you see the adhesion of the particularly the biological components are taking place on different surfaces. So, let us consider the interaction between macroscopic body, because of course, this adhesion and cohesions are governed by the intermolecular interactions, but if you see at macroscopic level, it looks like there is a interaction between two different macroscopic body, and if we assume the presence of only van der Waals interactions. So, we will take two cases. In one case, we are considering the two spheres of different radius r1 and r2, and in between their distance is the d. So, in this case the work of adhesion is, or you can say the energy is defined as minus A upon 6 d r1 into r2 divided by r1 plus r2. Similarly, if the work is defined, we can calculate force as minus A upon 6 d square r1 r2 divided by R1 plus R2. Force can also be calculated in terms of if W132 work of adhesion is known, it can also calculated from the work of adhesion into 2 pi r. 2 pi r into the work of adhesion, that is the R1 R2 divided by R1 plus R2. So, this is particularly if we are considering two hard spheres, they are coming are two macromolecules of different radii R1 and R2. Here A is the constant, A is the constant. Now, if you are considering a sphere on a solid surface, here we consider the sphere and sphere, we are considering we are having a surface, flat surface, and a spherical macromolecules is interacting with it, and different distance between them is d. So, energy will be minus A r upon 6 d, and similarly the force will be minus A r upon 6 d square, and force can also be calculated if the work of adhesion is known. So, 2 pi r into W, W is the work of adhesion here. So, adhesion of solid particle, we will just see example of one case. So, what it says, in case of solid particle adhesion, F adhesion is 2 pi r, here r we are considering two particles. So, R1 into R2 divided by R1 plus R2 into the work of adhesion, and work of adhesion here is the W132, means two bodies 1 and 2 are interacting in the medium 3. 132 means two bodies are interacting in the medium 3. Now, if you consider R1 and R2 are the equal, so F will be 2 pi r gamma solid liquid, because they are interacting in the liquid. So, this will be the solid liquid interfacial tension. If two identical spheres in the vacuum, so this will be the gamma solid vapor interfacial tension, 2 pi r gamma solid vapor interfacial tension. Now, if the sphere on a flat surface in the vacuum, there were two identical spheres. Now, if they are interacting on a flat surface, so here the flat surface, the surface work of adhesion will be the twice of the surface tension. So, it will be the 4 pi r gamma solid vapor, or you can say surface tension solid and vapor in the vacuum. And again, if it is there in any medium, it may be vapor or it may be the liquid. So, accordingly the surface energy will be there, either solid vapor or the solid liquid. So, in this way we should be able to calculate the force. So, here in here this is showing, this one is the spherical biomacromolecule and 2 is your surface. So, to study this system, Johnson, Kendall and Roberts, they proposed the basis of modern adhesion mechanics or contact mechanics, and that is why this is known as the JKR theory. JKR theory means Johnson, Kendall and Robert. So, what it suggests is the real particles are not completely uniform, or you cannot say they are not completely rigid and deform elastically under external applied load and attractive forces, giving rise to finite contact area under the external load. So, if we just consider this case, so there is a deformation in the sphere. So, this deformation, this dotted line, it may be due to any applied force F, or even it may be the attractive forces between the solid and surface and the sphere. So, in any case because of the presence of external forces or external load F, there may be the deformation and the rigid structure may not be there. So, what it says is, if there is a deformation, so this is the deformation line. So, it is considering a adhesion between the sphere and the solid surface. So, that is known as the JKR. JKR means Johnson, Kendall and Roberts theory, but at the same time if you just see here, only up to here it is coming in the contact, but from here to here it is not in the contact, it is, you can say, non adhering. So, that is known as the Hertz surface or the Hertz area. So, there are two things. JKR says it is completely deformed. So, this will be the A contact radius or the contact length A, and in case of Hertz layer the contact will be very much smaller. It says only partly it is touching on the surface, mostly it is not adhering. So, first we will see in case of JKR theory, there are two spheres here, R1 and R2, they are having the same elastic modulus K, and surface work of adhesion is given as the W12, external force is the F, radius A at mechanical equilibrium will be defined as A cube is R upon K under bracket 3 by 2 pi R W work of adhesion plus minus, here we are adding the force, here we are adding the, along with the adhesion force we are adding the external force, whatever F is applied, F plus 3 by 2 pi R W. So, in this case the contact, you can say the radius A depends on the value of the F. Now, in the same, if you want to shift this system between two spheres to the solid and sphere. So, what you have to consider, if R2 is infinite, R2 is infinite means it one sphere is considered as the flat surface, then we can write R1 as a R, and in this case W will be, work of adhesion will be twice of the gamma solid vapor. So, in this case we can write A naught, we are writing A naught here, A naught equal to, A naught means again here again we are considering in F is equal to 0. So, if you put F is equal to 0, so A naught will be coming out to be 6 pi R square W upon K, and W you can replace as the twice of the gamma solid vapor. So, it will be 12 pi R square gamma solid vapor upon K to the power cube. So, in this way if you are considering the two sphere, we should be able to know what is the this contact length A. Also the same expression can be tuned if you consider R2 as a infinite, means we are considering one sphere as a flat surface. So, adhesion force can be calculated by pulling the sphere with an external force that is equal to the force of adhesion. Thus, force of adhesion is minus 3 by 2 pi R W R between the two spheres. So, you can write W is the twice of the gamma S B. So, it will be like 3 pi R to gamma S B. So, in this way you should be able to calculate the adhesion force if R is known and the surface tension is known. Now, as I told, the Hertz surface considers there is a no adhesion, means only very small adhesion, and in this region there is no adhesion between the two particles between the sphere and the solid flat surface. So, if there is a not adhering means work of adhesion will be 0 and gamma will be 0. So, we say the adhesion force is considered to be 0. In that case, the contact radius is simply Rf upon k. It is very much simple, R into F upon k, R F upon k. So, this value comes out to be very small in case of Cartesian limit, or you can say the Hertz surface. So, these are the this is one example we discussed through the JPK theory, where we are considering the interaction between the two spheres, or you can say the interaction between a flat surface and a sphere. So, it is going to have the two different layers, this JKR layer, or you can say the Hertz layer, and there is a difference observations, or you can say there is some sort of deformation at the interface. So, there are going to be some hysteresis, and here like the contact angle hysteresis, we call it as a adhesion hysteresis. So, this is very similar to the contact angle hysteresis. So, interacting solid surface can have advancing and receding contact areas. This is axis is the contact area. If you just see this, let us consider in case of JKR theory. So, in case of this is the line, it is following for the advancing, but when it is coming for the receding, there is a difference in the contact area. Same we can observe for the Hertz layer as well, there is a difference in the contact area. So, this difference in the contact area suggests there is a hysteresis, and this hysteresis is indicating that there is some deformation at the interface. So, I have listed a few common example, especially the polymeric materials show the hysteresis due to the chain interdigitating across the contact area with time. So, polymers have different chains and they try to interact with each other at the interface. In case of metal and inorganic solid, the hysteresis is observed due to the some sort of chemical sintering reactions at the surface is taking place. So, whenever any such reactions are taking place at the interface, the adhesion energy, or you can say the loading energy, is less than that of the receding or unloading energy, and this phenomena is known as the hysteresis. If you remember the last when we talked about the contact angle hysteresis, so it was saying there is some sort of chemical heterogeneity, or there is sort of physical heterogeneity, or some change in the surface energy due to adsorption of the foreign molecules results in the contact angle hysteresis. Similarly, in case of adhesion hysteresis, some interactions are taking place. In case of polymer, because of its presence of the chain. In case of metals or the inorganic solids, the presence of some ions or some functional group, they are affecting, or the say there is some change in the properties of the interface. So, this is going to create sort of difference between the loading energy and the unloading energy, and we are going to see the difference in the contact area, that is hysteresis. Now, we consider the adhesion on a flat surface, but if you just see here, in actual whatever surface we will take, it may have the nano roughness, it may have the micro roughness. So, we are going to have some sort of rough surfaces. For the deformations of a rough adhesion junction of RMS roughness sigma, asperity contact may act as JKR junction with radius much smaller than the macroscopic particle radius r. So, if you are having the rough surface, let us say this is the surface, it is having some roughness, your sphere also you are considering the sub roughness, and its root mean square roughness is q, sometimes sigma, sometimes this sigma is also referred as RQ. RQ means root mean square roughness. So, if it is interacting, so what it says, the for deformation of a rough adhesive function of RMS roughness, the contact acts, here we are considering the R is very less than the capital R, the adhesion force will be F adhesion is F adhesion 0, 0 means the for the flat surface, and this is exponentially related with the RMS roughness. So, this sigma 0 is the constant, F adhesion 0 is the JPK adhesion force for the smooth surface, flat smooth surface, and why the repulsive part it becomes the exponential. So, this we can say exponential RMS roughness is again. So, what it says is, if we are there is some sort of roughness and the surface, it is again going to affect the adhesion force. Similar we observed for the contact angle. So, in the contact angle what we observed was, in case of surface roughness, we are going to see either decrease or increase in the contact angle depending on the initial contact angle. Similarly, and that was related with the Benzal equation. Similarly, here for the smooth surface, whatever the adhesion force was there, again we are going to add a exponential term of the RMS roughness. So, that way this adhesion force for the rough surface is going to change. So, I will conclude this lecture here. So, today we discussed about the cohesion and adhesion. So, in cohesion we start with interaction between two liquids A and B. So, we saw there is a change in the interfacial area of A as well as the interfacial area of the B, as well as the change in the area of the interface, change in the area of A, area of B as well as area of the interface, and A and B are the negatively related. So, from there we calculated the spreading of the one liquid over the other, and what we observed was, in case of water, hexane to the higher alcohols are going to wet the surface, but if you go for the diiodomethane and other carbon disulfides, they are having negative value of the spreading coefficient, means there will be no spreading. Also we saw once the two liquids are coming, so there will be the mutual saturation. So, in case of mutual saturation, the surface energy of the one liquid is going to change, and simultaneously the surface energy of the other liquid is also going to change because of the change in the purity or the change in its composition. So, we observed the water was having the surface energy of 72.8, and after mutually saturated with the benzene, or its surface energy decreased to 62.2. Then next we saw the adhesion means solid liquid interface defined by the Young's equation in terms of contact angle. Again we saw the how we can calculate the spreading coefficient, and here the same rule applies, that if a spreading coefficient is greater than 0 there will be the spreading, and if it is less than 0 there will be no complete spreading on the surface. Then we just quickly discussed few examples of adhesion, particularly in the biological systems. Then we try to relate the adhesion with this intermolecular interaction, particularly we consider the van der Waals forces, but here rather than intermolecular forces we consider the, because adhesion is taking between the macroscopic particles. So, we consider the macroscopic two spheres, or you can say the one sphere on a solid surface. So, to define the adhesion theory, we discussed the two theory, one was the JKR and other was the Hertz theory. In JKR says there is a adhesion and deformation, Hertz says there is a very non-adhesion and there is a very minimum contact between the either two spheres or the sphere and the solid surface. Then we, because of some deformation of the interface, we observed there will be change in the contact area for both the layers, either we consider for the Hertz layer or we consider for the JKR layer, and because of change in the contact area we are going to see change in the adhesion, work of adhesion force, or you can say energy, and that refers as the adhesion hysteresis. And then further we saw in actual whatever we consider either sphere or the surface, they are not going to be smooth. They may have the nano roughness or they may have the micro roughness, and we consider that adhesion force is related to the exponential of the RMS roughness. Thank you.